In this video, I will be explaining linear discriminant analysis in comparison with our logistic regression, and so that we will take the brief review of what we have studied in logistic regression. We saw that in the logistic regression is a classification technique in which the class labels are assigned by using one function called sigmoid function, and this is the sigmoid function which is here uh, reciprocal of 1 plus e to the power of minus z, and here the z takes the value of a simple linear regression equation, that is minus beta 0 beta 0 plus beta 1 times x, where x is the training data set, and logistic regression is a supervisory machine learning algorithm in which training data set is available. The value of sigmoid function is interpreted as the value of a probability of an observation x belonging to the class labeled 1. So this is the interpretation of this output value of a sigmoid function. If this interpreted probability value is greater than some critical value, then the class label 1 is assigned, otherwise the 0 is assigned. The performance of logistic regression or any classification algorithm in general is evaluated with the help of certain performance metrics. Here, the performance metrics that we have studied in our previous lecture was recall, precision, accuracy, fourth is the F1 square, and fifth was the ROC. So these are the 5 different performance metrics that are used typically to evaluate any classification algorithm. Now, about linear discriminant analysis machine learning algorithm, the LDA, which is shortly known as the LDA is the supervisory machine learning algorithm, and this supervisory machine learning algorithm takes a training data set. And for this, to illustrate the working of the LDA, I am using the training data set that we have used for logistic regression, in which we are trying to classify whether a particular person is suffering from coronary heart disease or CHD based upon given the age of that person. And here we have a sample data set of 24 different persons with varying age which can suffer from the coronary heart disease. The linear discriminant analysis algorithm works uh, on the Bayes theorem. Works on many probability mm, properties or the concepts from the probability theory. We are going to review those probability theory that is required to understand the working of LDA here. The LDA makes use of the Bayes theorem. I think you have studied the Bayes theorem in your probability and statistics course, which is nothing but a way to calculate the conditional probability. A conditional probability helps us to find the probability of a random event when certain evidence is available with us to calculate the or to determine the probability of occurring a random event. Here the probability of occurring a random event A is calculated when evidence B is available, which is equal to probability conditional probability of B when A is available times probability of A divided by probability of B. So this is the Bayes theorem in general. We are going to make use of this Bayes theorem in our LDA. The another concept that we are going to use from the probability theory is the prior probability. Prior probability in case of the classification situation is the denoted here by the symbol pi k, where k is the number of classification labels that are available, that are used to classify the observations. In case of the binary classification, k is usually 2, and which takes value 0 and 1. So the uh, probability of a randomly selected observation belong pi 0 means that probability of randomly selected observation belonging to class 0, and pi 1 means that the probability of a randomly selected observation belonging to class 1. So here the in this particular example we have calculated the probability of pi 0 and pi 1, which is equal to 0.8 and 0.2, because we have 24 number of instances in our data set. Out of 24 those instances, 19 instances belongs to the class 0, like this, class 0, and that's why the probability of pi 0, probability of taking a random observation belonging to class 0 is 0.8, and whereas the probability of randomly selected observation belonging to class 1 is 0.2, because there are 5 number of instances are there, and out of 24 there are 5 instances. That's why 5 divided by 24 comes to be 0.2. So that is the way in which we calculate the probability, prior probability. Another concept that we are going to use from the probability theory is the density function. Density function is basically again a typical kind of conditional probability. I am here using the describing the density function in the context of classification problem, and in the context of the classification problem, the density function is denoted by the symbol f subscript k of x, where x is an observation or random event. It calculates the conditional probability of a randomly selected observation has value equal to x, a particular value, provided that it belongs to the class k, which may take in the binary case 0 and the 1 value. So that is the meaning of the density function. The posterior probability is another probability that is we are going to use in the LDA, and that posterior probability is again the conditional probability, and it is the conditional probability of a randomly selected event belonging to class k, provided that a given observation x. Now let us try to understand the differences between these different probabilities: prior probability, density probability, and functional probability. Unlike a density function and the posterior probability, prior probability is not a conditional probability. Prior probability is the simple probability of a randomly selected observation belonging to class K. Density function and the posterior probability are both the conditional probability. The density probability calculates the probability of a randomly selected observation has exactly value x, like here in this case. See here, here I have given one example, that the probability of randomly selected observation has value 36, age equal to 36, provided that when the class K means that a person, we know that a person is suffering from the coronary heart disease. What is the probability that the person has exactly age equal to 36-year old? And that we have calculated here from our data set, because there are two observations are there of a probability of randomly selected person having age equal to 36 has 2 divided by 24. Because there are two persons in the our data set that has exactly equal to age 36. And out of these two persons, there is only one person is suffering from the coronary heart disease, and that's why a randomly selected person having age equal to 36, provided he or she is suffering from the coronary heart disease, then this probability is 1 by 24. So this is the density function. In case of the posterior probability, we are calculating the probability of a person of an observation having uh, belongs to a particular class K, which may be in case of the binary classification 0 or 1, having exactly when the age value of age is given. So that is called as the posterior probability. And in case of the logistic regression algorithm, we have calculated the posterior probability using logistic regression. Now, using some sigmoid function. In case of the LDA, we are going to use a theorem called Bayes theorem. See, here is the one of the most important difference between the logistic regression and LDA is that in case of the logistic regression, we have calculated the posterior probability using uh, sigmoid function, and in case of the LDA, we are calculating the posterior probability indirectly by using the Bayes theorem. And how it is calculated, let us see. The posterior probability is given by is nothing but the randomly selected observation belongs to class K. Means that we want to find the observation, whether we want to classify whether the given observation is suffering from the CHD or not. And so here the given is the age is the value. So it is calculated like the probability of X having age equal to a particular age, and it belongs and its class times probability of a person belonging to class K divided by the probability of that observation has the value X, and this is calculated in this way. This can be calculated in this way. The first is nothing but the conditional probability. Sorry, the probability of X equal to having value exact probability of randomly selected event has the value X, provided that Y equal to K is nothing but this is nothing but the density function, and this is nothing but the pi k, and this is also nothing but the f density function, and this can be calculated by using this equation. Now, what it is very easy to calculate the pi k. We have seen how to calculate the pi k, but we need to calculate the density function. And here, important thing that we want to know that if we somehow we were able to calculate the density function, then we can calculate the posterior probability. That is the classification probability. It is also known as the classification probability from the density function. And this is the way in which the LDA calculates the uh, kind of classification probability or the posterior probability using density function. That is the important difference between the logistic regression and the LDA. In the logistic regression, uh, we are calculating the classification probability by using some sigmoid function. Here we are using it as a density function. And now, this density function is associated with the is a property of some population and sample. Like there are measures like centrality measures are there in case of the statistical properties like age, mean, average, then standard deviation. Like this, the density function is a property that is associated with the sample data, and the population data that is available with us, and we can estimate the density function for a population if we have some sample data set. In our case, the sample data set is nothing but the training data set, and population data set is nothing but the large problem that in which we are going to apply our machine learning algorithm. Now, if the this population has is the Gaussian distribution. Gaussian distribution means that whether it has this bell-shaped curve, then that is called as the Gaussian distribution. If the population is the Gaussian distribution, then the density function is calculated is given by this expression. This expression involve is makes use of a prior probability pi. We have seen how the prior probability pi is calculated, where pi is the prior probability. Then mu k is nothing but the mean of the observation belonging to class k. Here our sample data set involves k classes. Means that if there are binary classification, there are two classes are there. If there are we are label if in multi-class classification problem, the k may be greater than 2, which may be 3, 4, 5, or 10, and we need to group our data set as per the class level, and we need to calculate the mean and variance of observations belonging to individual classes, and that is denoted by mu k and sigma k. So this is the meaning of mu k and the sigma k. When in order to calculate the posterior probability, we need to substitute or plug in this density function in this equation. If we substitute this density function in this equation, which we have derived from the Bayes theorem, then we can find the posterior probability or the classification probability. Now here, what I did is that I substituted the density function. This is the density function, and this is also the density function in the equation that we have derived from the Bayes theorem, and we get this very large equation. And we can see that in this equation, this classification probability or the posterior probability is denoted by p subscript k times x, which I have converted this equality into the proportionality. Means that this equation depends largely on this broad term, that is nothing but the density function. Here, what I am saying that the posterior probability is directly proportional to the pi k. What is the pi k? Pi k is our prior probability. Posterior probability is directly proportional to the prior probability times density function. And this equation now, this equality now I have converted into the proportionality. In case of this now, after taking the log of this proportionality, I get this expression. Log times posterior probability is directly proportional to log of prior probability minus log of under root of 2 pi sigma minus 1 by 2 sigma square x minus mu k square. So this is the equation that I got after taking the log of this equation. See here what I did on this slide. I have substituted the density function in the equation that we have derived from the Bayes theorem. I converted that equality into the proportionality, and third step that I did here, I have taken the log of this proportionality. Now this is the equation that I have copied from the previous slide. Here the 2 minus log of 2 under root of 2 pi sigma is a constant term which can be merged into the proportionality constant, and this equation can be simplified in this way. And I have expanded this square term in this, which is equal to x square minus 2 2x mu k plus mu k square. And after expanding, after multiplying this bracket by 2 sigma square, I get this equation. And here I can simplify this equation also, and which come x mu k divided by sigma square, x mu k divided by sigma square. And here what again I did that this term is not the class dependent, because there is no term in this term, there is no term is present which refers to the class level k. So this can be considered as a constant term, and again it can be merged into the proportionality constant. And this term, these two terms mu k, this term, this first term, and this is the second term, completely depends upon the uh, class labels. So that's why that cannot be merged into the proportionality constant. And when this proportionality again is converted into equality, uh, this becomes the equation like this. Delta k, here the delta k is nothing but I am calling it as the linear discriminant function, linear LDF, or linear discriminant function. And linear discriminant function is equal to x mu k divided by sigma square, that is the second term in this equation, minus mu k square by sigma 2 square, this is the first term in this equation, and this is the third term in this equation, from this equation. So this equation is now called as the linear discriminant function. Now in this here I have copied the linear discriminant function from the previous slide. I am explaining the individual term. Here the mu k is nothing but our estimated mean for class k, and how it is calculated. Here it is calculated the sum of all observations that are belonging to a particular class k divided by the number of observations that belongs to that class. So this is the way in which you can calculate the estimated mean of class k, or the mu k. Mu k is present in this equation, or the density function. How the variance is calculated, that is the sigma k square. The sigma k square is calculated like this: 1 divided by n minus k, where the big K is nothing but the number of class labels. In case of binary classification, it is 2. And it is the sum of k equal to 1 to, you need to calculate the variance by using this equation. Then estimated pi k are nothing but the prior probability. It is also called as the prior probability, and it is calculated like this. So all this calculation are now I am going to give you explaining by giving one example. Now this is the data set that we have got in our CHD data set, in which there are age is one variable, and we are predicting from the age whether we are classifying whether that particular observation belongs to coronary heart disease or not. So we got 24 data sets, 24 observations, and those out of those 24 observations, the 19 observations belongs to class k equal to 0, and 5 observations belong to class k equal to 1. Now see here what I divided all our data set into two classes, because it is a binary classification, and there are 19 observations belongs to class 0, and means that the person is not suffering from the coronary heart disease. 5 observations are in the belongs to class 1, means that those person suffers from the coronary heart disease. And now for this grouping, I need to calculate mu k. Mu k is nothing but average. Then sigma is nothing but our variance, and uh, probability pi 0. Here mu 0, average of all these ages is 30.78. Then variance I have calculated by this formula, then variance is equal to 60.53. And because there are 19 observations out of 24 from our total data set, pi 0 becomes 0.8 here. Now, similarly, average for the class 1 I have calculated here. There are 5 observations are there. Average of these 5 different ages is 37.6. This is the variance 144.24, and 5 divided by 24 comes to be the our pi 1, that is 0.2. And once you got these different values like mu 0, sigma square, pi 0, so mu 0, sigma square, and pi need to be calculated for both classes, class 0 and class 1. So this is the for class 0, and these are the values for class 1. Now once you got these values, you need to calculate two different density functions values, delta 0, delta 0 and delta 1 for a given observation. Like for suppose example, I need to calculate for the given observation is 36. So 32 suppose, and for 32 I have calculated like this by substituting these various values in this different function. When you substitute these different values in this density function, you get one particular value like this. And this is nothing but our help us to decide whether a particular observation is belong to class 1 and class 0. Now, the logic that we are going to use for deciding to assign the class label either 0 or 1 is that a density function having greatest value for the class, that class is assigned. Here the for the delta 0 of 32 is greater than delta 1 of 32, and that's why the class 0 is assigned. Now, this is the way in which we use the density function to predict the class labels in using linear discriminant analysis. Here I am summarizing the working of the linear discriminant analysis again. The linear discriminant analysis is a supervisory machine learning algorithm. Like logistic regression, the linear discriminant analysis calculates the posterior probability. But in case of the LDA, the posterior probability is calculated using the Bayes theorem and the density function of a population or a sample data set. And we are making use of a density function to label the to classify the observation. An observation is classified as a class K if it has the value of the density function greater than all the class labels. So this is all about the linear discriminant analysis. Thank you.